WebCodecs. Thank you for having us. Um, I'm actually not the only presenter. I'm going to share the stage with my co-editors. But the simple introduction slide is that this is a new low-level decoding and coding API. If you're familiar with the analogs and other platforms, be it Media Foundation on Windows or Media Codec on Android or AV Foundation on Mac OS, FFmpeg, this is in that space. It is an API kind of modeled on those and exposing those APIs actually to the web. I'll go ahead and hand it over to Bernard to talk a little bit about use cases or motivations.
Thanks, Chris. To start off, I'd like to use streaming as an illustration of an application that uses the browser for decoding in order to show how WebCodecs fits in. Streaming architectures have a few elements in common. The media is acquired by a server. For cloud gaming, this is typically via screen capture from a virtual machine running a game. Then the media is encoded, containerized, and sent to the browser. The transport could be conventional streaming over HLS or Dash, could be low latency streaming over WebRTC data channel, or streaming over WebSockets or web transport. The browser then receives the media, decodes and renders it, as well as sending mouse, keyboard, or game console input back to the server. In addition to APIs used for media transport, these architectures also rely upon media source extensions, MSE, and for applications requiring low latency, such as cloud gaming, low latency MSE is used. Next slide. So what architectural changes are required when WebCodecs is introduced? Well, WebCodecs is substituted for MSE. None of the other blocks need to change. WebCodecs supports container formats and works with any transport. Next slide. So what are the benefits of WebCodecs? As we mentioned, WebCodecs is transport agnostic. It works with any transport. Since low latency operation is inherent and fully specified, application developers don't have to familiarize themselves with the browser's specific differences introduced by low latency MSE support. WebCodecs leverages the GPU and supports dedicated workers, which MSE currently does not, which improves performance on lower end hardware and enables processing of raw video for effects or machine learning. In scenarios where encoding is done on the browser, WebCodecs offers access to advanced video features such as scalable video coding. Simulcast can also be supported by creating multiple encoders. Since WebCodecs is a low-level API, the application can control aspects such as recovery and concealment on the receiver side or rate adaptation on the sender side. In the interest of full disclosure, there are a few current limitations. WebCodecs support for AV1 and H.264 ABC with temporal scalability is work in progress, and DRM is currently not supported. Back to you, Chris.
All right, thank you so much. So I just want to do three quick slides or two quick slides on the API shape to make it real. So let's start off with the video side. You manage rendering of the video yourself by painting frames to canvas. Video frames are a canvas image source. So here you can see I'm using draw image. You could alternatively use text image 2D, text sub image 3D, where all of the canvas image source compatible APIs. So here's a decoder being instantiated. The output callback is that paint frame to canvas function I defined in the previous slide. This is a very simple configuration. There are a lot more knobs in the config dictionary, but just for the sake of brevity here, it's just the one. And then I'm calling decode. So you call decode, you can decode as much as you want, queue up as much work. The API is designed with kind of a fire and forget style. When the outputs are ready, they will asynchronously call the output callback. With that, I'm going to hand it over to Paul to talk about audio stuff.
So over the years, there's been quite a lot of issues when it comes to audio asset decoding, especially with web games. In particular, there was no progress, so we don't know how long an asset is going to take to decode. You can't cancel when you've started to decode. You have to decode everything in one go, so the file needs to be a complete file. If it's a soundtrack that is 3 minutes long, everything needs to be decoded ahead of time. That slows down the game start, for example. And then you'd have a very big in-memory PCM buffer, resident memory for all the audio assets. So the soundtrack, all the dialogues, and all the sound effects that we use a lot of memory for no good reason. So instead, WebCodecs is essentially the opposite of all that. It's very low level, doesn't make assumption about what you're going to be doing. And it's supposed to let you do anything that you would do in native, but it's going to use the codecs that are present already in the web browser, instead of having to compile, let's say, FFmpeg or libopus or whatever, and ship that as part of as your WASM code. So it's gonna integrate well with shared array buffer, audio buffer if you want to use directly WebAudio API. And the goal is to allow other formats than float 32 planar, for example, in16, which essentially halves your memory footprint. But you can go lower and you can do other things. Next slide, please. So I've got two use cases that I know are very used quite a lot when it comes to game engines, regardless of whether it is on the web or in native, console, PC, doesn't matter. So for example, you want to do progressive rendering of a very long audio track, but you want sample accurate looping. So you want it to loop absolutely perfectly, but you don't want everything in memory at once. So what you do is you decode progressively, you stick your decoded audio samples in ring buffer, you play them out, and then you loop around and you decode as you go, right? So you have a very limited amount of PCM data in memory at all time. And you can post-process in the worker, for example. So let's say you decode an opus file at 48K, but you want to render at 44.1K, then you would do your assembling there. And that's what we do in native, so log-free, in fact, wait-free ring buffer. That's using the audio worklet, so it's going to be extremely low latency, as low as the platform can go. And this is using, so if the slides are available later, there are two links, an article that explains the pattern and a library that is already used in production that implements that for you. So this is the case where, yeah, you want to render your soundtrack or your ambient sound or that kind of thing with low latency. It's no more expensive than doing it high latency, since you have low latency sound elsewhere in the game anyways. Next slide, please. Then the other scenario or use case we can have is when you want to decode audio, but instead of copying and being being wait free, you'd rather really minimize the amount of memory used, and you want to transfer buffers instead. So you can decode some audio to PCM via the methods that Chris presented, and then immediately post message the resulting buffer to the audio worklet for your rendering. But this doesn't copy, it's just you essentially send the pointer to the other side. So that's going to be very useful as well to limit copies. Some games have problems with memory burst pressure, and that can help. But that's only two use cases that we think will be useful for games, on top of the advantages that I explained in the first slide. That's it. Was that you, Chris, or Bernard?
Sorry, I forgot I was muted. One last thing to mention, I didn't know where to throw this in. It's important that we be able to get video frames and audio frames from user media. So WebCodecs is integrating with another specification that provides frames from user media tracks. This is the media stream track processor interface. You have a readable stream here of video frames or audio frames, and then you can use that to encode user media.